podcast is brought to you by LMU Munich.
Okay, so as promised, today's lecture is going to start with Euclid. I'll mention something about the other references in a few minutes. So one of the things we remember from ancient Greek geometry is the classification of regular solids. Okay, so there's a cube. And now I need a tetrahedron. So if you take every other vertex of the cube, how does it go? So if I do this, and then connect them all to the back edge, back vertex, I get a regular tetrahedron. Okay, hopefully that's clear. So here I have a regular tetrahedron. And the vertices in my regular tetrahedron, well, the standard way to write down a regular cube is to use plus or minus 1 as the coordinates of the vertices. So the vertices of this regular tetrahedron, as I've written it, are 1, 1, 1, and then 1, 1, minus 1, 1, minus 1, 1, and minus 1, 1, 1. So they're the vertices of my regular tetrahedron. And by the way, there's some other ones that go with the cube. So things like 1 minus 1. No, I did this. No, I need 2 minus signs. Sorry. I need 2 minus signs. There we go. The ones that go with the cube just have 1 minus sign or all 3 minus signs. So there are other ones. Which together with the things from the tetrahedron give all the minus signs. So I want to write down the symmetries of the tetrahedron. And the symmetries are pretty obvious from the figure. One of the symmetries is the permutation of the coordinates. Right? This has been set up so that this is invariant under permutation, and any of these, there's a single 1 and 2 minus 1, so if I permute cyclically, then I end up with a symmetry. And the other ones are 180-degree rotations on any axis. So I've written down for you generators of what's called the tetrahedral group. It's a subgroup of SO3, a finite subgroup of SO3, which is the group of symmetries of the tetrahedron. Well, we all know that SO3 is not simply connected. The spinner is not a representation of that group. You have to take a double cover, and in this case it's SU2. So there's this double cover SU2 to SO3, and my group G bar should have some kind of lift to a finite subgroup of SU2. And I want to write it down explicitly for you. And so to do that, I'm going to choose a map from C2 to C3, which is kind of well adapted to this problem. And my map is, okay, so I have too many pieces of paper, and hopefully I'll always find the right one when I need it. My map is ST goes to S squared minus T squared, I times S squared plus T squared, and 2ST. And I made those choices so that if I take the sum of squares of the things in the image, I get 0. So the standard quadratic form on my three-dimensional space is preserved by this transformation. Okay, so now I have to figure out how to lift a 180-degree rotation from this three-dimensional space to this two-dimensional space. And my claim is that if I take, first of all, ST goes to T minus S, then it's not hard to see what happens here. This changes sign, this stays the same, and this changes sign. So that's the 180-degree rotation, minus 1, 1, minus 1, in the three variables. If I take ST goes to e to the I theta s e to the minus I theta t. This one's slightly more work, but it's not hard to show that the matrix for this is cos 2 theta minus sine 2 theta, sine 2 theta, cos 2 theta, and 1 in those coordinates. So by an appropriate choice of theta, I can get another 180-degree rotation. And then the permutations of S and T induce some map that's obviously computable in terms of these three-dimensional coordinates. So I'll be permuting these three quantities cyclically. Sorry, if I permute these three quantities cyclically, I could write down a matrix for you that induces that permutation. If you really care, it's 1 over root 2 times e to the 5 pi I over 8 e to the, I'm not sure we care, e to the 5 pi I over 8. I'm not going to use this form, e to the 3 pi I over 8 and e to the 7 pi I over 8. But anyway, you can lift it. That would be the permutation. That corresponds to 0, 1, 0, 1, 1. OK. So why am I doing this? Well, I mentioned that complex codimension 2 singularities, we could get examples of those by taking orbifolds. We're interested in singularities which are appropriate for Calabi-Yau compactification. And so that means that in this case of two-dimensional singularities, the holomorphic 2 form should be preserved. So I want something not just in U of 2, but in SU2. By the way, it's a finite group, so it can always be put in the maximal compact. A priori, I would have been using GL2C, but I can work in the maximal compact. And I want to preserve the holomorphic 2 form, so I put it in SU2. So this is an example. So I want to study the singular space C2 mod G. And I'll do this by the standard methods of algebraic geometry. As I was mentioning yesterday, the key point in algebraic geometry is that we need to write down the algebraic functions associated to this space. And here, even though it's singular, we can do that. What I need to do is take the polynomial functions on the original C2 and consider the ones which are invariant under the group. So this will be the ring of functions, ring of algebraic functions on C2 mod G. And I'm going to calculate it for you. So let's see. So first I want to take a subgroup. So G contains, to get that 180-degree rotation with this kind of cos 2 theta business, I actually need to use a 90-degree rotation here. So I need to point out that G contains the transformation ST goes to IS minus IT. That's how I'm going to get one of my 180-degree rotations. And so I have to write down quantities which are invariant under this action. And it's pretty easy to do it. S to the 4th, T to the 4th, and ST are obviously invariant. And it's pretty elementary to check that any polynomial which is invariant under that group action has to be a multiple, has to be in the algebra generated by these polynomials. Not hard to do. What I want to do, I'm going to make some choices to make the eventual answer. My answer, cleverly, will have no coefficients. But, of course, if I hadn't made these choices, I would have coefficients. So I'm going to make a slightly different choice, which is to take the sum and difference here in my invariants. And then there's an algebraic relation among these invariants. In this case, well, to recover S to the 4th, I should do U plus V. To recover T to the 4th, I should do U minus V. That's S to the 4th, T to the 4th, so it's the 4th power of W. So that's U squared minus V squared. So that's how I compute the invariance for this particular guy. There's a slight generalization. Let me just mention, if I had done e to the st goes to e to the 2 pi I over ns, e to the minus 2 pi I over nt, then the invariance would have been, the analogs would have been half s to the n plus t to the n, half s to the n minus t to the n, and w, which is st. Same thing would have worked. And you would discover that u squared minus v squared equals w to the n. This is the type of relation that I'm after. This tells me how to describe the quotient as an algebraic variety. The functions on it will be polynomial functions in u, v, and w, but you have to mod out by this relation. W to the n minus u squared plus v squared is the typical kind of relation that you have to mod out by, and that describes the corresponding singular space as an algebraic variety. Okay, but I've got more to do. G also contains the transformation which takes st to, as I said over here, t minus s. And if you look on my current invariants u, v, and w, u is left alone by this. V, since t and s are swapped, gets sent to its negative. And w, the product, gets also sent to its negative. So the action of this second generator on the invariance under the first one goes like that. And the invariants for that are not hard to see. So I still got u as an invariant. I've got v squared, w squared, and vw. Let me give those some names. Alpha, beta, and gamma. Of course, I have the relation alpha beta equals gamma squared. But there's another, I also still have this earlier relation. And this earlier relation allows me to solve for alpha in terms of other stuff. V squared is u squared minus w to the fourth. W to the fourth is beta squared. So in terms of the invariance I'm now looking at is u squared minus beta squared. So I don't really need the alpha. And I can write my relation a little more compactly as beta times u squared minus beta squared. By the way, I could have done a similar thing over here. I could have included also, with this much of an action, I could have included st goes to t minus s and gotten exactly the same expressions, exactly the same sorts of things happened with the u, v, and w. The only difference is that when I solved for alpha, it's v squared, which is u squared minus, and now n had better be even. So this works if it's beta to the n over 2, if n is even. And then I would have gotten an equation, gamma squared equals beta times u squared minus beta to the n over 2. And that's another example where I'm taking the group. So this time it was the group, the cyclic group of order n generated by this guy. Here it's a group generated by z mod 2n and also this other transformation, this guy with matrix 0, 1, minus 1, 0. If I took that subgroup of SUN, I would have gotten this equation. So I got one equation, two equation. Those are two infinite series of equations which are related to the steps that I just encountered. But for my tetrahedral group, sorry, I need to raise the board a bit for everybody to see. For my tetrahedral group, I've still got one more thing to do. So the last thing to do was this permutation. Right? I wanted to permute the three quantities. I could plug in this matrix, but I don't really have the stomach for that. I can permute these three quantities instead. And even that is slightly unpleasant. So let me point out that u, my quantity u here, which is one of my current invariants, is s squared minus t squared squared minus I s squared plus t squared squared divided by 4. And the advantage of writing it that way is that I wrote it in terms of quantities that are here. So I can cyclically permute. And that's going to go to something which, in the end of the day, turns out to be minus a half u minus 3/2 beta. And beta, I'm not going to do the whole calculation for you, but it's trivial to do. Beta is just 2st quantity squared divided by 4. And that goes to, again, cyclically, that one's going to go to s squared minus t squared squared divided by 4. And if you write that in terms of the current invariance, that's equal to 1/2 u minus 1/2 beta. And I should say that gamma is actually invariant under this particular cyclic permutation. If you write out what gamma is, v times w, it's a half st. If I write that in factored form, s squared plus t squared, s squared minus t squared, that's got all three quantities here that are being permuted multiplied together, so it's obviously invariant. So my cyclic permutation has now been expressed in terms of my current invariants u beta and gamma. And to write down the invariance, this is it was a cyclic permutation of order 3, so those two funny quantities, u and beta, should be involved with eigenvectors somehow. And it turns out that beta plus or minus 1 over root minus 3u goes to, again, not hard to see from those formulas, minus a half minus or plus root minus 3 over 2 beta plus minus a half minus or plus root minus 3 over 2 times plus or minus 1 over root minus 3u, so that these two quantities are eigenvectors with eigenvalues to two primitive third roots of unity. That's the same sort of thing that I was doing invariance for before. And so the invariance for this action can be written down as so I still have my gamma from before. Sorry, no wonder. Okay, this gamma, I beg your pardon, but gamma has to be called z. Alpha, beta, gamma was too logical. Any place else? I think that's it. Right here. Thank you. Okay. I think I've expunged the gamma. All right. So now my invariants are gamma, which is half beta plus u over root minus 3 cubed plus a half beta minus u over root minus 3 cubed. It's the same thing same trick I was doing before. Y, which is the difference of these guys, difference of the cubes. And I'm going to call it minus x, which is the product. So the relation that I get immediately is minus x cubed is equal to gamma plus y times gamma minus y, which is gamma squared minus y squared. And of course, I still have my z, which is an invariant. And in fact, if you write out what gamma is, so when I take the sum of these two quantities, I end up with the every other term in the binomial expansion, right, because of the plus and minus sign. And so the two terms that I get are the first term beta cubed, and then the next term, which is plus 3 times 1 over root minus 3 squared times beta u squared. So that's beta cubed minus beta u squared, and that's the equation I already have for z squared. Well, up to a sign, so it's minus z squared. Okay, so I don't need this invariant. I can get away with x, y, and z. And I can substitute in place of gamma, I can substitute minus z squared. So I get an equation here, which in the end of the day turns out to be y squared equals, putting the y on that side and the x on this side, x cubed plus e to the 4th. So that's what I meant about miraculously no coefficients at the end. I had to work pretty hard so that everything was defined so that I would get this equation. Okay, so in 20 minutes, which I told somebody I could do it in 20 minutes, I was right, In 20 minutes, I've sort of started with one of the standard Euclidean rotation groups, and I've derived the invariance and explained to you which algebraic variety I got as the invariance of this thing. And along the way, we found two infinite families of groups, and we ended up with equations for those infinite families of groups as well. What if I want to do the cube? Well, the symmetries of the cube are the same as the symmetries of the tetrahedron with one additional thing. Namely, I get to do 90-degree rotations on the axes, not just 45-degree rotations. And it's not hard to see that all the 90-degree rotations are conjugate to each other within the tetrahedral symmetry group. That kind of makes sense because it's the other set of vertices which form another regular tetrahedron. So if it did one 90-degree rotation, I would be mapping to that other set of vertices. So for the cube symmetries, I also have to include e to the st goes to e to the 2 pi I over 8 s e to the minus 2 pi I over 8t. And let's just chase that through. So I'm doing cube roots, eighth roots of unity, so the fourth powers change sign. So I get a sign change on these guys. I get a sign change on these guys, but the product is the same. So UVW, under that symmetry, mapped to minus U, minus V, and W. Now let's see, for alpha, beta, Z. So alpha was V squared, that's left invariant. Beta was W squared, that's left invariant. VW changes sign. So alpha, beta, V, Z rather. The alpha and the beta got left alone, and the Z changed sign. U is also changing sign. And so my last one is these gamma, Y, and X. So beta is not changing sign, but U is changing sign. So these two guys get swapped, but that doesn't change gamma. However, swapping these two guys changes the sign of Y. Swapping these two guys does not change X. So X, Y, and gamma, the only thing that changed was the sign of Y. So of my X, Y, and Z, my final coordinates, the final invariance into the whole group, X had its sign, X got left alone, Y had its sign change, Z had its sign change. So the new invariants are, let's see, so X is left alone. I'm going to call capital Z equal X. I need some more room. So what am I doing invariance? I have capital Z, which is little x. I have capital W, which is little y squared. I have capital Y, which is little yz. I have capital X, which is z squared. I already know that y squared, that's W, can be written in terms of other things. W is x cubed plus z to the fourth. Those are lowercase. This is capital Z cubed plus capital X squared, so I don't really need the capital W in my invariance. And from here, from these three, the obvious invariant is y squared equals xw, which now is x times x squared plus z cubed, or x cubed plus z cubed x equals y squared. That's the equation of invariance for the group of the cube, called the octahedral group. It gets named after its dual figure usually, instead of by the cube. So let's see, what groups did I have here and here? This was just the rotations, so that's, there are these two infinite families of groups which aren't acting on regular solids, but are really two-dimensional. So this is rotations. This is the group of rotations plus reflection. That the lift of the reflection from SO3 to SU2 is this element 0, 1, minus 1, 0. And then there are 5 Platonic solids, but one of them is self-dual. The other come in 2 dual pairs, right? The tetrahedron is self-dual, but the cube and the octahedron are dual. So I've got 2 out of 3 symmetry groups. The other symmetry group is in SO3, it's the octahedral symmetry group. Lifted to SU2, it's called the binary octahedral group. And I'm sorry, I can't build it up nicely out of this line of events. I'd have to spend another half an hour to derive its invariance, so I'm not going to do that one. So I did all but one case in 25 minutes and gave you all of the invariants for these guys. So that's orbifold singularities. The third reference up there, this paper by Alan Durfee, is called 15 Characterizations of Rational Double Points. These singularities are known in the mathematics literature as rational double points, and as the title of his paper suggests, there are 15 independent ways of saying what they are. In other words, some property that characterizes singularities turns out to characterize this class of singularities. So orbifold singularities from a subgroup of SU2 is the first characterization, but there are lots of other characterizations. The orbifold one I started with partly because I talked about orbifolds last time. We get an orbifold metric because it's an orbifold on all these singularities. It's not at all obvious when you write down an equation like that you would have gotten an orbifold metric. There are characterizations in terms of the equations themselves, but one of the nicest characterizations has to do with blowing up. So I'm now going to do the two ways of studying these singularities that I described in general last time and that we did for codimension 1 singularities. I'm going to resolve the singularities, and then I'm going to deform the singularities. And I'm only going to do the resolution explicitly for this tetrahedral case. So this is the binary tetrahedral group. Binary just means I lifted it to SU2. So this is the case where my equation is y squared equals x cubed plus z to the fourth. So I'm thinking of that as defining something inside of C3. So this is now the C3 with coordinates x, y, and z. When I went through the Puiseux expansion last time, I introduced new coordinates. I didn't really tell you what I was doing in introducing the new coordinates, but what I was doing was a special case of what I'm about to do now, which is that we need to blow up C3 at the singular point. So what does blowing up mean? Well, if I want to blow up C3 at the origin, I'm going to take my x, y, z space, and I'm going to replace it with 3 different coordinate charts. In fact, intrinsically, what I'm doing is I'm going to take a pair consisting of a point x and a projective point c sitting in C3 cross P2 with the property that the projective equivalence class, this should be it, vectors also, projective equivalence class of x, I don't know if that really gets a vector symbol, who knows, is C. So that does absolutely nothing away from the origin, but at the origin it replaces the origin by an entire copy of P2. And as usual, we'll need 3 coordinate charts to represent it as P2. Sorry, I've got to find my blow-up page here, or else I'm in deep trouble. Here we go. Right, so I could do x1, z1, y1, z1, and z1, or 3 other choices. X something, y something, and y something, z something, or x something else, x something else, y something else, and x something else, z something else. The reason I'm not committing myself to indices here is I need all the indices I can get for future choices. But this choice of indices I want. So blowing it up, I'm starting out with some singular point. You know, it's hard to draw what the singular point might look like because it's a surface singularity. But anyway, it's some kind of singular point. And I'll be replacing the origin with a copy of P2, which I have no choice but to really represent as a line here. And then my singular guy will pass someplace through that line, maybe at more than one point, depending on the structure here, and I might still have a further singularity. I might have to blow up some more. So the strategy is that you blow up until you're done. And one of the interesting characterizations of rational double points is they are things which can be blown up and you never, so there are, in general, if you have a hypersurface singularity, you might have to do two steps. One is a blow up, and the second is a step analogous to the Puiseux series expansion that we were doing yesterday, called normalization. And that second step never has to be done. And that actually characterizes the singularity. So in some funny sense, the blow-up I'm going to do is not quite representative of general blow-ups exactly because I'm doing the interesting case for surface singularities, the rational double points. OK, so this is my first blow-up. I'm going to choose the z coordinate chart, the third coordinate chart on the P2, and do the blow-up. And that means that I'm just required to substitute in for my changed coordinates. But then I can pull out a common factor of z1 squared in this case, common factor of whatever highest power of the new coordinate I got. And that leaves me with this singular point in the first chart. Well, what I've done, in fact, is replaced the origin by the entire locus z1 equals 0. And if I want to know where that z1 equals 0 lives on my new surface, I should intersect with z1 equals 0. And that's called the exceptional divisor. So the exceptional divisor for this first blow-up, E1, it's the intersection of z1 equals 0 with my equation, y1 squared equals whatever. But really, it's just z1 equals y1 equals 0. So I've got an exceptional divisor. It looks like a copy of C in this coordinate chart. If you examined all the coordinate charts, you would find that it was P1. It's a linear P1 in the P2, and there it is. So that's the first blow-up. On that P1, I now have a single additional singular point of my surface. So that P1 is contained in the surface. I should really stress that I have my new surface. It's got the P1 in it, and it still has a singular point someplace at that surface, which I've identified explicitly as the origin here. Sometimes when you do this, you have a singular point not at the origin. Again, I've prepared coordinates cleverly so that this computation looks a lot easier than it really is. If you don't make all the choices so well, it may be trickier. Let me go to a second coordinate chart, and this time I'm going to use x. So I want y1 to be x2, y2, x1 to be x2, and z1 to be x2, z2. So a complete writing out of this would have involved 3 coordinate charts the first time. Then, luckily, this singularity, since it's at the origin in this coordinate chart, is only present in one of those 3 coordinate charts. But one of them should be replaced by 3 others. And I have to blow up one more time. I'll have to do 3 more. So you would have this horrible collection of coordinate charts to completely describe it. And I'm being very selective. And I'll make some claims to you about what happens in the coordinate charts that I'm not showing you. But we'll see all of the important action happening here. So I'm going to substitute and also factor out x2 squared at the same time. So I'll get y2 squared is, the total degree of this term is 4, so I'm going to get 4 x2s. That leaves me with 2 of them. And this term has degree 2, so I'll just end up with my z2 squared. So this time I have an exceptional divisor, E2, given by x2 equals 0. And E2, therefore, looks like x2 equals 0 and y2 squared equals z2 squared. So it really has 2 components. It has E2 plus, which has y2 equals z2. And it also has E2 minus, which has y2 equals minus z2. So let me try to draw what just happened. I have my two exceptional divisors that are created by this blow-up. My previous exceptional divisor was at z1 equals y1 equals 0, and so that's still visible here as z2 equal y2 equals 0. The E1 is actually still passing through that intersection point. So there's E1, here's E2 plus, here's E2 minus, and that's the picture. And this guy, by the way, I'm recognizing singularities just by looking for linear terms at the origin. I don't see any, so it's got to be singular there. Again, a complete treatment would involve looking to see if there were any other places where the thing were singular. So you'd have to compute all the partial derivatives and see where they had common zeros. But in this particular case, the origin is the only thing happening. And again, I do x. So y2 is x3, y3. x2 is x3. z2 is x3, z3. I've got y3 squared is, total degree is 3. This time has gone down. You subtract 2 for what I'm factoring out, so that's x3, z3. And then I have z3 squared. So still singular, one more time. The exceptional divisor, again, is going to split up. E3 plus or minus will be the set where x3 is 0. Right, and y3 is plus or minus z3. Now, what's tricky is that the E2 plus or minus had x2 equals 0, and I used the x here in this coordinate chart, and that means that the old x2 equals 0 stuff is not visible at all. So E2 minus and E2 plus have sort of gone out of my picture. The picture that I just ended up with is still my original E1. Now I've got an E3 plus and an E3 minus. So that's what's visible here. And I'm just going to assert to you that the E3 plus meets the E2 plus back in some other chart, and the E3 minus meets the E2 minus back in some other chart. So that's the current picture that I have after this blow-up. And there's one more blow-up to do. Here I have a quadratic equation which has maximal rank. It's not hard to see that if I have a quadratic equation with maximal rank, when I do the blow-up this time, the exceptional set, it's been lines up till now, but this time it's going to be the degree 2 non-singular quadratic that's defined by this equation. So I'll end up with a single exceptional divisor. It doesn't really matter which chart I use to describe it, and I'm going to avoid using any chart to save myself time in the computation. What I end up with is an E4. The E1 is poking out of one point. The E3 plus pokes out of another point. And the E3 minus pokes out of yet another point. And then, as I said, I've got my E2 plus and my E2 minus coming along for the ride. And that turns out to be non-singular. So I'm actually done at this point. So I derived the equation for you from the group theory. And then I, with a few flicks of the wrist blowing up, managed to get the entire singularity resolved. So those lines, again, represent P1s. Now, there's a traditional way of representing this data, which is to introduce a dot for each of the exceptional divisors. Maybe they should be labeled by other geometric data. For example, they might have a higher genus. The degree of the normal bundle in the surface is an important piece of information that people often keep track of. But for right now, I'm just going to put dots here. And then you join two dots when the corresponding curves meet. It's not obvious, but it could have happened that curves met more than once or something like that. So maybe I would use multiple connections if there were multiple intersections. But in this case, there's just a single intersection. And I end up with a picture like this. How many people do not recognize that diagram? Okay, so this is called the E6 diagram. And for that reason, we give it the name of the E6 singularity. Let's see. In the middle of this, I had things, I could have rewritten this as z2 plus a half x2 squared minus a quarter x2 to the fourth. And the only reason for pointing that out is that it's a square equals a square plus a higher power. And that was actually what was going on in these last steps of the process. And sort of using that reasoning, you can pretty quickly see what happens to this set of guys. Each blow up, except possibly the last, introduces a couple of exceptional divisors. You might have another couple of exceptional divisors, another couple of exceptional divisors. Until you're done, right? And at the end, you're either going to get one or two. So the final result is some kind of chain of curves like this. And if I make, by the way, there are n minus 1 curves for this particular equation, u squared minus v squared equals w to the n. And so if I make the corresponding graph, I end up with what's called the an minus 1 graph. So an minus 1 is the name that's usually given to this singularity, and it corresponded to the cyclic group Zn sitting inside of SU2. These singularities generate the D diagrams, and that's a harder computation, so I won't try to explain to you why it happens. But you end up with Dn diagrams from this family, z squared equals beta times u squared minus beta to the n over 2. Well, let me say dm and beta to the n over 2, so I don't have to think about how to match those labels. I get dm diagrams from that. I just got the E6. And then it turns out that E7 corresponds to the binary octahedral, the one that I wrote down at the very end up there. So we could blow that one up and we would get an E7 diagram. And then E8, the Dickin diagram E8, corresponds to the binary icosahedral. So Euclid's classification, actually they're called Platonic solids. Maybe it's due to Plato instead of Euclid. Anyway, the classification of solids from three-dimensional geometry corresponds to these three exceptional Dickin diagrams. And then the other finite subgroups of SU2 correspond to the two infinite series, the AN and the DN series. You'll notice I'm only getting simply laced diagrams from this picture. So there's a one-to-one correspondence between the simply laced diagrams and the singularities, the rational double point singularities. So let me state a theorem. One of these characterizations. So theorem, if x in some x is an isolated two-dimensional singular point, such that there is a rank 1 sheaf. I think I can say locally free. Well, let me just say rank 1 sheaf. L near x such that L restricted to x minus x is the canonical divisor, canonical bundle, then x in x is isomorphic. Well, this is isomorphic maybe in the analytic category, so after analytic change of coordinates, to one of these rational double points that we're discussing, in other words, AN, DN, or EN, E6, E7, E8. the rational double points we've just discussed. So although I started out with orbifold singularities, this condition says that the canonical bundle of the surface is behaving well near the point. Sorry, one more condition. And if I had a resolution, then pi upper star of this sheaf has a section with only zeros. Well, it has a non-vanishing section. So I want something which resolves to be a Calabi-Yau surface, something with trivial canonical bundle near the surface. And this is exactly the class of singularities which have that property. So one thing which I didn't show, but which you could check with these explicit coordinates, is that if I were to have taken ds wedge dt and pushed it forward into the invariant ring in some natural way, I would have got some object which wasn't very well defined at the singular point, but if I pulled it back to this resolution, I would have had a nowhere vanishing section of that particular object, all through these coordinate charts. Okay, so now I want to do the deformation theory for these guys. And again, I'll focus on E6, on the binary tetrahedral case, just to have an explicit example. That was my E7. So my equation is y squared equals x cubed plus z to the fourth. And the deformations are given by, well, naturally enough, by deforming the equation, adding on some other terms of the equation. And by another result from that book of Milner's that we discussed last time, I can actually determine those things by taking the ring Cxyz and modding out by the partial derivatives of the equation, partial of f with respect to x, y, and z. For example, the partial of f with respect to y is 2y, so I'm in this little finite ring here of possible choices for deformation. I'm not going to include a y term or anything divisible by y. And the reason for that is pretty clear. That one we know, right? If I had a y squared and then y times anything, f of x, y, z, well, let me just say f of x and z, I could have made a change of coordinates, something like y plus a half f squared, to get rid of that y term. So that's an informal way of explaining why things from these partial derivatives aren't really required. So for this particular case, the things that I leave out are y, x squared, and z cubed. And that leaves me with not too many choices of monomial. I have the constant term. I have so the reason I'm writing it slowly is that I'm going to want in a second to do something. Let me just tell you what I'm about to do. So I want to choose a weighting on those variables, a little bit analogous to what happened in the Puiseux expansion examples last time. I want to choose a weighting on those variables to make the whole thing quasi-homogeneous. And so the least common multiple of these exponents is 12. I could take y to have weight 6, x to have weight 4, and z to have weight 3. So I'm going to put my z first, and then I'm going to put a y, then I'm going to put a z squared. I didn't leave enough room. Z, y. So this has weight 3. This has weight. This y is an x. This has weight 4. Z squared has weight 6. Xz has weight 7. And x squared has weight 8. And now I'm going to put a subscript on the coefficient to make the total weight come up to 12. So I've done something wrong. X squared is not what I wanted. Z cubed is what I wanted. So what am I missing? Xz squared, thank you. Xz squared is weight 10. Very good. So this is a 2. This is a 5. This is a 6. This is an 8. This is a 9. And by the time I put the coefficient, I don't really need the 1. That's a 12. So there is a deformation. And there's a little bit of theory here, which tells you that any deformation that you might have written down in any number of variables could actually be induced from this one. So in other words, I could take the AJs to be functions of some other variables. That would give me a way of taking, this is called a universal deformation. It's actually called a versal deformation. It doesn't quite have a uniqueness property, so people dropped the uni from the word universal. It's called a versal deformation, and it has the property that if you had any family whatsoever, you'd be able to find AJ as a function of the parameters to turn the deformation into this form. So there's my deformation, and in some sense that does the deformation theory, but I need a little more information than that. For example, I'd like to know something about the monodromy transformations and so on. And so for doing that, I need to outline for you an extremely beautiful piece of theory with respect to these rational double points. Oh, before I do that, however, let me mention one way of getting at this parameterization. So, and this refers to both, I've already mentioned the Durfee, has all the characterizations. The Ljujenka and the Kronheimer had the following sort of point of view. So Ljujenka's point of view is that I should take this object omega, which is the deformed holomorphic 2 form, which I should consider everywhere away from singularities of this guy. So now in the entire family, I could write down, in principle, I could write down some messy expression in the A's, which would dictate where this thing was singular. It's mostly non-singular. So if I stay away from there, I could imagine integrating over the cycles gamma in the Milnor fiber and get some kind of information about periods of that holomorphic 2 form. In Kroneker's formulation, Kroneker looked at a symplectic structure for this guy and did the basically same construction, looked at the periods for the symplectic structure. So if you do these integrals, of course, we're expecting some kind of monodromy on the Milnor fiber. So there's a monodromy group, which I'm going to call W. And if I were to take these quantities, but then mod out by W, in other words, sort of take the W invariant expressions in those guys, I would end up with the, so, sorry, maybe I should have taken a polynomial ring with these as coefficients and then taken the W invariant expressions. I would have ended up with exactly my polynomial ring in 2, 5, 6, 8, 9, 12. 8, 9, 12. I would have ended up with a polynomial ring in exactly these variables. So you can recover this by studying period integrals of these guys modulo monodromy. And there's a way of kind of getting at this explicitly by looking at a Picard-Fuchs equation for these period integrals. And the Picard-Fuchs equation for these period integrals, which will depend, it'll be a PDE with 6 variables, right? And it exhibits this full monodromy W. OK, I'm finally going to erase my references. So I've told you about everything except the last 3. Maybe I'll leave the last 3 for a minute. So here's the beautiful result. It's called the simultaneous resolution. Simultaneous resolution of rational double points. And the names associated to this are Grothendieck, Brieskorn, and Tirana. it says that if I go up to this space represented by the periods, so I've got my C6, or in general my CR for the rank, with my AJs, and I've got some other space, and then W is somehow acting as the quotient. So this is the quotient by W. This is some other space and some other variables, Bj. I take my versal family here, and I move my versal family up to here just by making this change of coordinates. So I'll say in a second exactly what this change of coordinates is, but there's some nice change of coordinates with the property that you can now blow up, V tilde can be blown up so that every surface is resolved. Every surface in the deformed family is resolved, yet each fiber of the resolution is a surface. So let me explain what the issue is. If I took the very simplest singular point, x squared plus y squared plus z squared, and put in a deformation parameter t, like those a's over there, I would end up with a non-singular threefold, which had a singular surface at t equals 0, but a non-singular surface elsewhere. And if I attempted to blow up that singular point on the surface, I would blow up a singular point on the threefold. So right now I've got this kind of nice picture of a singular curve on a non-singular threefold. If I blow up the point, I end up with not only my surface, but another component sitting in the middle there. That's what we want to avoid, is an irreducible surface. I should have said irreducible surface. So I want to avoid introducing other surface components. And in this particular simple case, if I make the change of variables t equals s squared, then I get what's the familiar conifold singularity. Hopefully this is visible to people. I get the familiar conifold singularity, which does have a so-called small resolution replacing the point with a P1. That small resolution has the effect of resolving the central fiber while not disturbing the nearby fibers, and it resolves it without introducing an extra surface component that I don't want in the story. So it's a really beautiful result, this simultaneous resolution of rational double points, and it's even more precise than I've written so far. Namely, the monodromy is given by the reflections. Yeah, so I guess I missed saying one or two things about the connection with the root system. So this connection with the root system, E6 in this case, is not completely coincidental. Each of the roots in the root system, so roots in the root system, such as E1 plus E2 plus E3, irreducible or not, right, whether it's one of the basis ones or not, correspond to curves C on S with the property that the canonical divisor of S dot C equals 0 and the self-intersection of C is minus 2. Moreover, the monodromies, and this is so these curves can all show up as vanishing cycles in the Milnor fiber. So all of them are vanishing cycles in the Milnor fiber. And as a consequence, there are monodromy transformations which take a general element x to x plus the intersection with this curve times the curve. That basic pattern for monodromy transformations. In other words, the monodromy transformations are reflections in elements of self-intersection minus 2 in the root lattice. And the group of reflections of self-intersection, well, let's see, in Lie theory, the self-intersection is 2 rather than minus 2. There's a sign difference between Lie theory and algebraic geometry. I'm sorry, in algebraic geometry, we can't change the sign. It's a natural topological sign, and so please, all Lie theorists change sign. We've been saying that for decades, and they haven't done it yet. So there's a sign difference. But anyway, the reflections that I just mentioned generate something very well known from Lie theory, namely the Weil group of the root system. And that's my monodromy group W that I mentioned over there. So the actual base change that you have to make is by the Weil group of the root system. And there's a really pretty story in which you have parameters in some space, and you mod out by, these are complex, well, this picture shows up in gauge theory, let me just mention. If you look at a Higgs mechanism, say in a supersymmetric gauge theory, which breaks the gauge group down to a Cartan torus, then you can label points according to essentially eigenvalues, but you have to mod out by permutations of eigenvalues. In the case of SUN, that's the symmetric group, which is the Weil group. In the case like E6, this is the analog of modding out by the eigenvalues and getting a sort of characteristic polynomial. So this is basically the analog of the eigenvalue, the elementary symmetric functions and the eigenvalue. And it always has a smooth parameter space modded out by this reflection group, giving you another smooth parameter space. And that's the one that we use for the basis of these, of this versal deformation. So the versal deformation is really powerful. It gives us all the information that we could want. And you can even be more explicit than I've been so far. So it's possible to write down the loci in the versal deformation space, which correspond to certain of these classes remaining algebraic curves as opposed to simply vanishing cycles in the Milnor fiber. That technology is explained in my paper with Sheldon Katz, AlgeGeom 9202002. That would be the second paper ever in AlgeGeom. It had just started, and we were trying to fill it up with stuff. So it's a slightly old paper at the time, but we put it in. Pardon? That might also be a paper of mine. Yeah. I started AlgeGeom, right, with Paul Ginsparg's help and encouragement, and I think 01 is a paper of mine, and 02 is the paper with Sheldon. Yeah, right. Now that I remember, the 01 paper also has a hep-TH number from 4 or 5 months before. That's not allowed anymore. Okay, where was I? So I've got my simultaneous resolution. That's the deformation theory, and it also contains the information about monodromy. And it's a very powerful tool. Let me just describe it, since I'm on the eigenvalue question. Let me describe it in this simpler case of the an-1 singularity. So there I have x squared plus y squared plus z to the n plus. Now it's familiar that I don't need the n-1 term in here, right? I do that kind of deformation. And my Cn-1 that I started out with the eigenvalue action can be described as a set of T1 through Tn. These are the eigenvalues of the matrix. And since it's special linear, sorry, this is the algebra maybe. Since it's special linear, the sum of those eigenvalues is 0. And the Weil group of an-1, which is the symmetric group on n letters, acts on this by permutations. So the jth coefficient here is simply the jth elementary symmetric function of T1 through Tn. So let me rewrite that as x squared plus y squared plus z to the n plus, sorry, maybe the n minus jth elementary symmetric function, sigma 2 of T1 up through Tn, z to the n minus 2, and so on. And of course, so that's when I make the base change. Of course, we know what that means. That means that we can rewrite this as the product of z plus tj, j equals 0 to n. when I've written the equation in that form, I can do a blow-up for it that's very analogous to the small resolution that you're, of the conifold that you're accustomed to. Really, I should have been using maybe UV here. Instead, it makes it easier. And now I can blow up something like U equals Z plus T1 equals 0. And then after that, I blow up U equals Z plus T2 equals 0, and so on. I produce a single rational curve, a second rational curve, a third rational curve. I do the corresponding small resolution all the way along the line, and end up with this picture that I've got after doing this change of variables to the from the elementary symmetric functions up to the t's. I'm able to do the small resolution. Okay, so that's kind of the example of how the small resolution business works. For the D cases, you can also write it down pretty explicitly. For E6, E7, and E8, it's pretty unpleasant to write explicitly. Sheldon and I in that paper were dealing with various explicit forms of the problem for E6, E7, and E8. A lot of what we had to do was teach a computer to manipulate invariant polynomials for that Weil group without ever multiplying them out, because 25 years ago, or 20 years ago, whenever we were doing this, for example, Maple wouldn't handle a polynomial with more than 10,000 terms. Silly Maple. Silly us for wanting to calculate with 10,000 term polynomials. So we found ways of avoiding complete calculation. Okay, so as a kind of application of this theory, I want to describe a couple of things. First, I want to go back to the F-theory situation that we had last time. So in the F-theory situation, I was dealing with a family of elliptic curves which looked like this. And now I'm going to assume that T is a single parameter. So I'm just going to do the simplest F-theory case for a moment and try to think about what kind of singularities I get from this story. So I mentioned that there was this, maybe I didn't mention, there's a classification of all the possible singular behaviors that can happen, which is due to Kodaira. And I sort of started telling you about the simplest kind of singularity last time. But now that we've got the sort of set of singularities we need under our belt, we can kind of go through and analyze what happens in a little more detail. And again, so I don't have time to state it carefully, but Durfee's characterizations tell you ways of looking at the polynomial and reading off what kinds of singular terms you have. So last time I mentioned that if I wrote down the discriminant, which would measure when there was a multiple root, the key question was whether it was a double or a triple root. And you could tell that it was a triple root exactly when T divided F, or if and only if T divides G. Right? So I'm assuming that T divides delta. And then I get a triple root if and only if that happens. So the double root case turns out to be the case where I end up with the in-1 singularities. I'm going to make a table. So in the table, I'm going to have, let me find out, make sure I don't skip a column. Wake up, computer. OK, I'm going to have the Kodaira type. So that's just some kind of notation. And the first one is called I sub n. And I'm going to measure the Kodaira type by the order of vanishing of F, the order of vanishing of G, and the order of vanishing of delta. Well, the first Kodaira type is the boring one, where delta doesn't vanish. I don't really care if these vanish. And the fiber looks like an actual elliptic curve. No problem. What else do I want in my table? The singularity of the total space, which is what we've just been studying, there isn't one. And I'm going to tell you about the monodromy for the elliptic fibration, and it's the identity. There's no monodromy either. So nothing happens there. So now we have this sort of main series where we have a double but not a triple root. And we're going to measure the behavior by looking at the order of the discriminant. And when you have a double but not a triple root, actually you should make a change of variables here to maybe put the double root at the origin. And you end up with an x cubed and an x squared and an x term. And you can actually see the structure of the rational double point. You ignore the x cubed term, you get the x squared terms in there, and then the order of vanishing of delta turns out to be exactly the power of, in my equation over there, w that occurs. So I end up with an an minus 1 singularity. And the fiber, we typically write like that. It's a fiber with a node. And here I definitely don't want f or g to vanish. And I mentioned last time what the monodromy is. The monodromy, there are two approaches to calculating the monodromy. One is I can write down the Picard-Fuchs equation for the family depending on f and g. It'll involve things like the partials of f and g, and I can read off the monodromy by techniques similar to the ones that Albrecht was discussing today. Or we could follow Kodaira's original approach, which was to use the singularity type to classify the fibers, to make an example of each of those by using the known possible finite order elements of SL2Z and draw a conclusion about what the monodromy had to be by comparing the singularity types. So there was a very indirect argument initially. Then we go into some cases where I have triple roots, and the simplest triple root case doesn't involve a singularity of the total space again. There's simply a triple root. It means that at t equals 0, I'm going to have y squared equals x cubed only. F has order, G has order exactly 1, F has order at least 1 in that particular case. And then I start to get a few more complicated guys. So it's a little boring, but all the rest of these are just these cusps. So the only fibers that ever occur are nodes and cusps. The singularity, the simplest singularity that could show up here, oh, sorry, I should, yeah, fiber of the resolution is what I'm meant to be drawing. So the fiber of the resolution is actually, it's got my an minus 1, but it's also got the remainder of the original elliptic curve. And what that gives me is something whose dual graph is an affine Dynkin diagram, an an minus 1 tilde Dynkin diagram. Here, the fiber on the resolution is two curves that are tangent to each other. There's an A1 singularity. This is a 1, and this is at least 2. 4, I've got 3 curves passing through the same point and an A2 singularity. Sorry, this is 2, 3, 4. And this should be 2 and at least 2. Sorry, I'll uncover the rest in a second. So here I have I0 star, where I don't, this is at least 2, at least 3, 6. And I end up with a D4 tilde and a D4 singularity. I guess I should fill in my monodromies before I erase the board. So, well, you know, maybe the important thing here is that there are some and that they can be looked up, right? I mean, I don't know that anybody's going to learn too much by copying these. But those are the monodromies in those cases. Oh, oops. Well, everybody memorized that one, right? So I n star has exactly 2, exactly 3, n plus 6. It has a dn tilde, n plus 4 tilde graph, and a dn plus 4 singularity, and the monodromy is -1 n 0 -1. And then I've got 4 star, 3 star, and 2 star. So for 4 star, this is 8, this is 4, and this is at least 3. And let me write for you what the equation looks like for 4 star. It looks like y squared equals x cubed plus, maybe there's an x term, I don't care, but the key thing is that the constant term is z to the 4th. That's the one we were just working out. So we recognize that as an E6 singularity. And it turns out that the extended Dickinson diagram is what you get for the fiber on the resolution. I'll look up the monodromies for this in a second. 3 star is 9, 3, and at least 5. And that has an equation, y squared equals x cubed plus, for the linear term, I've got z cubed x. And the equation that I erased right there just now, everybody remembered? It's this one. It's exactly this one in these variables. So that's E7. Well, I didn't blow that one out for you. The only one that we really checked in this story is E6. OK, can I quickly draw this? Yes, I can. OK, monodromy in a second. And this one turns out to be E8. So this is 10, 5, and at least 4. The E8 tilde graph, the E8, and some monodromies for these last 3. The monodromies are finite order in these last 3 cases and also in the 2, 3, 4 star case. -1, -1, 1, 0, 0, -1, 1, 0, and 0, -1, 1, 1. OK, so that's the story for everything about codimension 1 behavior in F theory, modeling the behavior of the elliptic fibration near the singular point. So there are a couple of things to say. The first thing to say is, from the F theory perspective, what I described for you last time was a collection of D7 branes. That was the case that corresponded to this monodromy transformation 1n01, and that looks like n D7 branes. So we understand that n D7 branes should be generating an SUN symmetry, and this is a singularity which is actually associated to that SUN symmetry. So it's not an accident that the gauge group is the same as the Dickinson diagram. There's a very beautiful story in non-perturbative string theory. So for example, I can take this elliptic fibration and put the type 2a string on the elliptic fibration. When I've done that, the D2 brane can wrap each of the cycles that are being represented by blowing down to get to the an-1 singularity. And that gives me a massive BPS object in the theory, and the mass is proportional to the area of the cycle. So I discussed blowing up so far as if it were this discrete operation. Actually, you might get that impression from the equations that I wrote down. But really, there's a size involved for each of the exceptional divisors. Cronheimer's point of view, which is one of the reasons I gave the reference to his, makes that very clear, that the size is an important parameter. So there's a size for each of these guys, and that size is proportional to the mass. Therefore, if I go to the limit in which I've blown these all down and gotten back to a singular spot, then I should expect to find a bunch of massless objects. Those end up carrying in the n equals, sorry, I'm in 8 dimensions. Those end up carrying also in the supermultiplet, those end up carrying a gauge field, and we've exactly created enough massless gauge fields to represent the off-diagonal elements in a non-abelian gauge group. So although the type 2 theory, M theory, most of the string theories other than heterotic does not produce naturally a non-abelian gauge symmetry if you use a non-singular variety for compactification. This argument goes back to 95, to the very earliest days of the second superstring revolution. This kind of singularity in these contexts does provide a non-abelian gauge symmetry. So I get a non-abelian gauge symmetry in these various cases. The other one that's easy to identify from the type 2b perspective comes if you look at the orientifold construction in type 2b. And then you discover that here you have an ND7s plus an orientifold plane, giving exactly the same amount of monodromy. So we have the sort of perturbative type 2b interpretation for two of the particular kinds of fiber. We have a general interpretation in terms of the total space for getting enhanced gauge symmetry. Now, I should also mention that, okay, so we had deficit angle 2 pi over 12. That actually means that you need 24 of these I sub n's, or it turns out that deficit angle in the other cases is measured by exactly the order of delta. So I could replace some of my I sub n's by a corresponding number of other singular fibers. And all of those singular fibers produce global solutions, K3 surfaces with an elliptic fibration and certain kinds of singular fibers. And it's all labeled by the same data that's used in K3 surfaces. And in a version of the type 2 heterotic correspondence that Albrecht went through yesterday, in fact, we get an F-theory heterotic correspondence between the heterotic theory on just T2 and the F-theory on elliptically fibered K3s. And when you look at this correspondence carefully, you discover that the same mechanism, namely classes in the lattice, well, depends on the sign that you put on things, but classes in the lattice of square minus 2 in my normalization correspond to rational curves of square minus 2 sitting in the fibers of an elliptic curve, and that means that they have to be part of one of these things in the Kodaira classification. You get exactly the same mechanism responsible for enhanced gauge symmetry on both sides of this story. So those things led people to believe that in the F-theory context, in the M-theory context, 1 dimension down, in the 2A context, 2 dimensions down, this was a really good construction for producing non-abelian gauge symmetry based on this particular type of singularity, complex codimension 1 singularities with the holomorphic top degree form well defined in a neighborhood. So these rational double point singularities. It leaves in the F-theory context these other cases, these cases with finite monodromy. And well, the I0 star case is interesting because there's no actual restriction on the value of tau in this case. So here, tau is arbitrary. But in the other cases, tau, or more precisely j, the invariant quantity, is completely fixed by the type of singularity. So this one, there's some hope of making models which have some kind of perturbative interpretation. Doing so is going to what's known as the Sen limit. There's some really interesting cases where you've got a limit in the moduli of all of the compactifications in which the I0 star having finite tau plays an important role. These other cases are definitely not ever going to be perturbative from the type 2b perspective, but we call them exotic F-theory branes of some kind. Different names are used for them, and try to investigate their properties. They're going to give rise to enhanced gauge symmetries, for example, of these exceptional types. So when you see a type 4 star fiber and an elliptic fibration, you recognize the singularity in the total space as being one that's going to give you E6 enhanced gauge symmetry. So in the 2B perspective, 2B context, we think that that's some kind of 4 star brane, whatever it is, an E6 brane, that gives us that kind of singularity. I think that's probably a good place to stop for today. Go ahead.
I guess IN star is 4 plus.
Thank you.
Yeah.
IN star is Yeah, number of D7 branes is wrong. Yeah, thank you. Yes?
If I look only at the monodromies, it seems that some of them can be written as combination of the others.
Well, that's certainly true. What I'm writing down, so these are monodromies up to conjugacy, I should say. And what I've written down is almost a complete list of conjugacy classes for monodromies in SL2Z. It's only missing a couple of things. Here, n was restricted to be non-negative, but there also are monodromy transformations where n is negative. And same thing is true for this one, n is restricted to be non-negative. So it's slightly mysterious why those conjugacy classes don't show up. But these are all of the conjugacy classes of so-called elliptic or hyperbolic, parabolic elements, excuse me, in the group SL2Z. And sure, I can write some of them as combinations of others. For example, I could imagine taking an elliptic fibration with just 3 singular fibers, a little bit analogous to the monodromy considerations that Albrecht had this morning. If I had a known monodromy around these two, then the product of those monodromies would tell me the monodromy around these, and that sort of gives me a way to predict what the third fiber would have to be if there were only 3 singular fibers.
And a further question? So if not, then let's think and Dave again.